Hello. So today we're on the Helios 650 and I'm going to attempt to demonstrate how we will do a targeted atom probe liftout on a grain boundary. And we're going to use the EDAX team software to do some TKD mapping of the atom probe tips to make sure that the grain boundary is right in the volume or in the finished volume on the sharpened atom probe tip. So we're going to go through the whole process here and I'll explain the steps as we go. And hopefully at the end we'll end up with 3 or 4 good atom probe tips. So let's see how it goes. I already have the sample in the chamber. This is a magnesium sample and it's in an epoxy mount. It's a rather large sample, so this is the only thing that's in the chamber right now. A lot of times I like to have the silicon posts or whatever you're going to drop the sample onto after we do the lift out. I like to have it in the chamber at the same time and save some time, but in this case, because this is so big, we're going to have to vent the chamber and put in those after the fact. So let's go ahead, we'll turn on the beam and we will find the sample. Now let's turn our beam current down a little bit. So epoxy mounts don't conduct very well. So this one has been grounded using a bunch of silver paint, which is what this material is. And unfortunately the nav cam on the Helios is not working right now, otherwise that would make it much easier to find the center of this sample. I guess if we just go to 0, we'll just go to 0, 0. And actually, we already did a lift out on this sample before, so I'm just going to use this spot as a starting point, and let's see what we can find. So we'll go ahead and focus. We'll link our working distance. Let's bring this up to 4 millimeters. And let's start hunting around. So just one thing to watch out for is whenever you're working near previous lift out sites, you know, there might be a lot of gallium implantation or ion beam damage. You can kind of see that here by this sort of hazy appearance, this bright white appearance around these pits. We would do well to stay away from this stuff. You know, that way we know we're not going to get a contaminated grain boundary. So let's move a little bit away from this spot. And we'll actually, before we do that, let's go back. I'm going to use one of those pits to find the eccentric height just because it makes it a lot easier. Nice big obvious feature. Here we'll use this little hole, put that right in the center, and let's do our stage tilt. Okay, should be good enough. All right, so let's go find a grain boundary and we'll see what we can see. Now this sample's been etched. You can see lots of grain boundaries already show up because of the etchant. But if you can't see those, sometimes it's helpful to use the backscatter detector. So just to demonstrate that, let's do that. We'll go electron beam here and we'll put in the CBS. Always watch out and make sure that you got plenty of clearance for the backscatter detector so that it doesn't crash into anything. And then let's just go to a little bit higher beam current. Let's check our alignment. So the backscatter detector doesn't like fast scanning. So you need to use nice and slow scans with this one. But you can see here the retractable backscatter detector, the CBS, does a really good job of showing the grains through the channeling contrast. So a lot of times if you have a sample that's not etched, it might just be really well polished. If you can't see any of the grain structure, I would say first thing to try would be the backscatter detector. Now let's pick two grains that are showing some different contrast here that should indicate that they're a little bit higher angle grain boundary. And this should make our life a little easier later on. Now, of course, you could do EBSD on this surface, and you could measure the orientations of all these grains, and we could try to target one of these specifically, but let's not worry too much about that right now. How about this one? These two grains have real big contrast differences. They're a little bit scratched up, and that's okay. And there's a pretty straight grain boundary here between the two. So I guess let's just try this one for now. So let's get a little bit better focus here. Now, one of the problems with the backscatter detector is that it won't let you use your gas injectors. So it can be tricky to identify where this grain is. Without any kind of indication. Like for example, here in this secondary electron image, you can see there's not a lot of contrast to show this boundary, but we can see it real well in the backscatter detector. So what I like to do is we can't actually insert the gas injector to do a deposition here, but what we can do is we can open the gas injector valve and we can basically contaminate this surface with the platinum or the carbon, and it'll leave behind a mark that we can then see with the SEM. So to do that, here let's kick up our beam current a little bit on the SEM. More beam current's always a good idea when you're doing SEM depositions. Let's make sure our focus is kind of reasonable. We don't need perfect focus, but okay. So now what we're going to do is we're going to draw our deposition, our pattern, and we're just going to choose none for the application file because I don't want it to actually try to insert a gas injector. And let's line up this pattern with the grain boundary. And let's choose our size. I'm going to try to make 4 atom probe tips. Each atom probe tip would be 2.5 micron by 2.5 micron square, so I need 4 of these in a row. So I'm going to do 2.5 times 4, which would be 10 microns by 2.5, and that's going to be our deposition. So we can zoom in here a little bit more. We don't need to be that low of a magnification. All right, and then let's put the pattern. We want to get this lined up as close as we can. Get it right there on that grain boundary. And let's just go set the time here so that it'll run for a couple minutes. So you could either set the Z value to something large like 3 microns. It's kind of meaningless here because we don't have an application file. Or we could just go in and set the time. So if I set the time to be like 3 minutes, 00 seconds, so that'll scan for 3 minutes. Now, what I want to do is I'm going to hit play. And when I do that, you see the SEM just starts rastering in that area, but there's nothing else is going on because the gas injector's not open. And then I'm going to go over here to the gas injector control, and I can't insert it. I don't want to insert it, but I'm just going to open the platinum injector. And I'm changing the brightness contrast a little bit here. Now what that'll do is in the the gas injector, the needle is retracted. It's up here on the near the SEM column, but the needle is open, so the gas is still being delivered into the chamber. It's just not a very efficient process. There's not a lot of gas coming down onto the sample, but as you can see here, there's enough of it. So as that's depositing, you see the backscatter image got really bright. And what that'll do is it'll create a really nice, obvious black square that'll show up on the sample. Makes it really easy to find this spot again once we retract the backscatter detector. So it's a good trick to keep in the back of your mind, that if you have a feature that you can only see with the backscatter detector in, you can still mark it with the gas injectors. Just you can't insert the gas injector. One thing I'll point out, there's a bug in the software. If you move the mouse over top of the gas injector control, in certain places, it'll generate an error. And let me see if I can get it. Yeah, like this. And you get this unhandled exception error. This won't cause any problems in the software, so just hit continue. If you hit quit, it's going to close the UI, and you're going to have to restart everything. So that only happens if you move the mouse over top of the insert area with the backscatter detector in. So what I usually try to do is kind of like go around the side to get over here to where the open and closed buttons are, and that way you won't generate that software bug. All right, we're getting a little bit of drift here. I'm going to beam shift slightly just to try to keep this right on that grain boundary. Now, because the application file is not controlling the deposition, when this timer finishes, it's not going to automatically close the gas injector. So I'm going to have to do that manually, but just double clicking on the word open down here. Okay, so the pattern's done. I got to go close the gas injector, and we can delete that pattern. So now if we start scanning again, we can see that we've now put down a nice little platinum spot, which, let's see if I adjust my brightness and contrast settings a little bit here. Obviously very, very easy to see a platinum deposition on magnesium, but the more important thing is that we can now see it with the normal Everhard Thornley secondary electron detector. And we'll also be able to see this with the FIB. So now we don't need our backscatter detector anymore. So let's go ahead and retract the CBS detector, and we'll move quad 2 back to the ion beam because that's what we'll do in a second. All right, so now we have a little bit of platinum on there, not a lot. I would say we definitely want some more just to make sure we don't get any contamination in the grain boundary when we go to do the FIB prep. But to do more deposition, we can insert the gas injector, and by having the gas injector right up close to the sample, it'll be much, much more efficient. So let's go ahead and we're going to insert the platinum injector. So here's the needle's in now, and we'll go ahead and, I guess I could have left that pattern on the screen earlier, but we're going to do a platinum EDEP structures, 10 micron by 2.5. And let's just do maybe 0.5 microns according to the file. Let's do more than that. Let's do like 1.5. I want this to run for a minute or two. The SEM depositions aren't very accurate, so you need to just kind of pick a time based on your previous experience and just go with it. All right, let's go ahead and rotate our pattern. stick it on there like so. And we'll go ahead and hit play. Oop, got a little bit of a shift there. Let's slide that over. So then this this platinum deposition will protect the grain boundary from the gallium implantation, because we're going to have to do another deposition on top of this using the FIB. And if you do a FIB deposition on an exposed grain boundary, generally the gallium will travel down the grain boundary, and you'll see that in the Atom Probe results later. Especially like samples like aluminum, you really have to protect the grain boundaries really well, because the gallium will just move through there super quick. All right, so let's go ahead and delete the pattern. Let's turn our SEM conditions down to something a little more reasonable, and we'll take out the gas injector. Let's go full screen. Fix our brightness, contrast, astigmatism. All right, now just because I would prefer to have this horizontal, I'm going to go ahead and rotate the stage. But if you have if the compucentric rotation is not really accurate on the stage, this thing may move a long way away, and it might take you a while to find it. So I always recommend, when you're doing this kind of procedure, is just save your stage position before you move it. That way, if you get lost, you can always come back here again. So let's use the align feature. We'll go ahead and make a line parallel to this and say make this horizontal. And in this case, it didn't move too far away, just about 30 microns, not too bad. But I've seen a case where the sample ends up on the other side of the chamber, and then you spend all day looking for this site again. Okay, so let's now, we're going to tilt to, and I'm just going to update this position now, because I know we're going to have to come back here again. So let's go to 52-degree tilt. And we'll add some more platinum on top of this using the FIB. The SEM platinum is okay to leave on there, but it's a little bit on the soft side. So you'll find, what I've found is that when you start doing your FIB cuts, you'll lose the SEM platinum a lot faster than the FIB platinum. So it's a good idea to have at least some of the FIB deposited platinum on top of there, just because it's a little bit of a harder capping layer. All right, so FIB, let's check out our FIB image first. Now, if the tool is aligned really well, my beam shift on the SEM is zeroed out, and I'm at the eccentric height. If I go and look at my FIB, and the FIB zeroed out, and I'm also, again, at the eccentric height and tilted, FIB should be looking right at this spot. So let's turn up the FIB magnification so it's similar to the SEM, and we'll take a snapshot. And I see nothing because I forgot to turn the beam on. Let's go ahead and turn the beam on. One of the most common questions I get from new users is they say, I can't see anything on the SEM or on the FIB, and it's because they forgot to turn the beam on. It happens to everyone. All right, so there's our snapshot image, and I can just see there's a little bit of the bottom of the deposition right up here at the top of the screen, so let's just beam shift that down. And there's our deposition. All right, so let's put in the platinum injector, and we can draw our pattern. So we're going to do PT dep 10 microns by 2.5 microns, and we're going to add another half a micron on there. Now, you have to remember to set the appropriate beam current based on the pattern area. So this is 10 micron times 2.5 micron. So we're at 25 square microns of area. And then we're going to use 6 picoamps of beam current for every square micron. So times 6 is 150. So 150 picoamps is what I want for my beam current. And in my list, I have 40 picoamp, 80 picoamp, and then it jumps up to 230. For Atom Probe samples, I would recommend you go to the lower beam current if you're in the middle between two, just to make sure you don't accidentally sputter away anything and cause some damage to the sample. Every time we change our beam current, always do a snapshot. You see there the image is shifted a little bit. Got to watch out for that. And if our focus is off a little bit, we can check our focus. Just don't scan on top of the platinum area. We want to keep that nice. Okay, so we're in focus. Make sure our pattern's lined up with not only with the platinum deposition from the SEM, but also with the grain boundary, because you can see the grain boundary here. We want to make sure maybe there was a little bit of a mistake with the platinum. So let's just make this right. I'm actually going to shift it a little bit because I think the SEM deposition drifted slightly. I want to be lined up right on the grain boundary, so I'm going to do something like this. A little bit of drift there. So it looks like we're a little bit off the left side of my deposition. So I'm just going to beam shift my FIB pattern area just to the right, just a little bit. Not that it's real critical. It's a big, long, straight grain boundary. If we end up a little bit to the left or the right, no big deal here. But sometimes it could be. That's better. Let's just check in here and take a snapshot, make sure everything's going well. Yep, so far so good. All right, so let's take out the gas injector, and we got our nice deposition there on the surface. Now, I wasn't planning to do this, but I think it's a good idea just for this training video. Is let's say is to demonstrate how to do this with the EBSD maps. So let's say hypothetically you can't see any of these grain boundaries with the backscatter detector, and you need to do this um, using the EBSD maps. So here, let me save my position, and then let's go over to open up the EBSD software, and let's configure the tool to do a quick EBSD map. So I'm going to go to 30 kV, and we'll go up to a nice high beam current, something like 13 nanoamps. And I haven't actually tried EBSD on this sample yet, so hopefully the polishing quality is good enough. If it doesn't work, it doesn't work, I suppose. Now, for EBSD, we want to get a high of tilt angle as we can, so we want to go to 60 degrees. I'm not quite sure if that's going to bump into the side of the column because this mount's so big. So what we want to do is lower our working distance quite a bit. So let's turn on compucentric tilt, and let's drop this down to like maybe 8 millimeter working distance, maybe 10. All right, so I can't go to 10. That's why it moved in a really weird way. So let's go back to the last position. Maybe we can go to 9. Let's go 9.5. Yeah, so 10 is just too far out. 9 is going to be the most we can do. And then let's go ahead and tilt to 60. And there, we didn't bump into the lens cap, which is good. All right, so let's get into reasonable focus here. I'm not looking for anything spectacular. This is just to demonstrate how this works. And let's just say save our position. So this is going to be EBSD. And so let me configure this so you can see what's going on here. We're going to see, let's see, lock this. Let's shrink this guy down into the corner. All right, so real quick, just so whole world watching this on YouTube doesn't know our login password. Let's go ahead and log in to EBSD. And we'll just say create new project and just call this magnesium APT test. New sample, magnesium. Identify the structures. Change everything to no. We want to add MG. Search magnesium. Okay. Okay. So I'm not going to go through all the rigorous detail of how to set up team, but I'm going to make sure everything's back to defaults. With the Huff, transform, we go to image area, make sure my tilt correction's on, make sure my pre-tilt angle is correct. So in this case 0, it's reading the stage tilt as 59.9, that's right. Go to the EBSD camera position, and we'll just say insert, and because it's at 59.9 instead of 60, team's yelling at me, but that's okay, just say yes. And we got to watch out, obviously, here on the CCD camera when the camera comes in. If it bumps the corner of the mount, we're going to scratch the EBSD phosphor. What I generally find is you want to watch your SEM image and hover your mouse over the stop button, which is down here in the bottom left, or the red button right here. But you'll see the SEM image move if the camera touches the sample, and to me it's way more obvious than trying to wait for the touch sensor to go off, or to see it here in the CCD camera. So I always like to just kind of zoom in to fairly high mag there, and if you see your sample all of a sudden go shooting off to the corner, then you know you just hit your camera, and that's usually a bad day. All right, so let's see if we can get this set up. So we'll go to EBSD camera. 4x4 binning's pretty good for this particular camera. Let's turn our image processing to none. Let's see, we need a little bit of gain, maybe something like this. And then let's go ahead and capture our background. Let me turn the frames up a little bit. Capture background, and then go to standard. Oop, too much. I got a little dead spot there. So I need to go back here, and let's turn the gain down slightly. Image processing, capture background. There we go. So now if I zoom in, if I park the beam on a grain, I should hopefully get a pattern, which kind of am. I think we need more intensity. Let's kick up the intensity. Let's go up to 51 nanoamps here. We're not going to melt the sample or anything. Sometimes when these samples don't diffract really great, you need more beam current. Yeah, it's not really any better. Anyway, let's see if we can get a quick map here. Maybe it'll work. So we'll go to mapping. And say let's take image area. And let's just do a custom. Yeah, let's try 10 by 10. Why not? And that did nothing. It was way too coarse. Let's try. Let's bring that down to like 2 microns. So we're getting a little bit of signal here. Not spectacular. One thing that hurts you with magnesium is it oxidizes really fast. So in this case, what I can do to get around that problem is I'm going to take out the EBSD camera for a second. We're going to say, where is it? Camera position, retract. And I don't need to let it, I don't need to take it all the way out, but that's fine. All right, and then let's go back to our position where the sample was underneath the FIB. And I'm going to kind of wreck some of the area around this spot, but I'm just going to kick up the beam current, and I'm just going to scan on this spot for a few seconds with the FIB. And the idea here is it's going to sputter away some of the junk. And you can see here my FIB image is getting really bright. All right, so now let's go back to our EBSD position. You can see here on my where I've cleaned this spot, right? So let's put the camera back in. Now there's still a lot of damage in this sample, but maybe we can at least get it to index. I can certainly go back and blast the surface with a little bit more more FIB current too. So that didn't really improve it much. But what I wanted to demonstrate here, I can see, so this grain boundary over here to the right was actually looking pretty good. So let me go in here and show you this. Let's zoom in on that boundary. And let's do another quick map here just to make sure I'm in the right spot. Okay, a little bit too fast of a step there. Let's drop this down to like 0.5. All right, so obviously there's a giant scratch going right through this grain boundary, which is not great, but you can see there that we've got, let me pull that map back up again. Basically you got red grain, yellow grain. Let's say you do all your data analysis and this is the grain boundary that you want to do for Atom Probe. How are you going to find this again later? Well, we can mark it with the platinum deposition. And the way that I do this is let's go back to our area. Oop, I want to go back to mapping. I'm going to go into my EBSD map and I'm going to make a freeform scan. And this just lets me draw kind of a weird little figure around here. So we're basically going to try to draw a map around there and say go. All right, so that's my area that I want to mark with the platinum. So let me, I don't think it's probably a good idea if we come back to the FIB UI here. I can put the gas injector in, which will kind of help, but the gas injector, some of these gas injectors will run into the EBSD camera. So like, especially the low angle ones like the carbon. The platinum one we can put in. It's not going to hit anything. But just like before, where I was scanning with the backscatter detector and I was injecting the platinum, I'm going to do the same thing here. Now the trick is I don't really have a way to slow the scanning down here except for making a really painfully small step size. So if I drop this step size down to something like 100 nanometers and hit collect map, even that's not really a really great slow scan. So I'm going to stop that, hit OK, hit finish. Let's go even smaller. Let's drop that down like by another factor of 4. So like we'll do like a 250. Because I want a scan that's going to take like a couple minutes to go over that area. That should be good. You can always run the scan multiple times. So now what we do is we're going to go into the software. We're going to pop open the platinum injector. So now the gas injector is running, and I'm going to hit collect map. And this will deposit just a little bit of platinum where the beam is scanning. So after a minute or so, when this map is done, we'll turn off the gas injector and take a look at the surface with the SEM, and hopefully there'll be a really obvious mark on this spot that we can then use for further FIB prep if this was the grain boundary we were looking for. So this is the approach I usually take if I need the EBSD map to find the grain, if there's no other way to find it. This works pretty well. This also has the added benefit of giving you the orientation relationship of the two grains, which in theory we can get that from the TKD work at the end when you do the atom probe sharpening, but it's always nice to get it two ways, I suppose. I think I might have made the step size a little on the small side here because this looks like it's going to take 17 minutes. It's a little bit longer than I want to wait. So I'm just going to say let's stop the map, finish. Let's just so we get a mark on here, let's run this back up to the 100 nanometers. I'll just say collect. And you see it's not indexing very well anymore. That's because it's all full of platinum probably. What does the camera image look like? Yeah, there's really, we've contaminated this spot with so much platinum that it doesn't diffract anymore, which is good. That's what we wanted to do. All right, so now let's we're going to retract. First, let's close the gas injector, retract the gas injector. Let's retract the EBSD camera. And if we take a look now with our SEM, let's see if there's any mark. Now, not a real obvious mark there because the FIB or the SEM is up at 30 kV. But if we drop our SEM back down to our more normal imaging conditions, all right, let's go back up to our FIB spot. Okay, so this is our site where we're kind of working on earlier. And if we look over here, probably should have done a little bit longer scanning, but at least you can kind of see where the mark is. If I go into, or not CBS, I want to be ETD backscatter mode. And you can see where that platinum was deposited. Now, if I did that with a smaller beam current than 51 nanoamps, it'd be a little bit prettier deposition. You can see there's a big halo around there. Probably should have just set up my EBSD map to run at maybe like 6 nanoamps or even 13 nanoamps, and I would have gotten a lot cleaner mark there. But if you, based on this mark and looking at this surfaces and the other stuff that you can see around here, you can compare it back to your EBSD map and stuff. This is probably enough information to at least find that grain boundary. All right, let's get back to what we were doing, which is, let's get out of backscatter mode. So the next thing we have to do, now that we've got our grain boundary protected, is we need to figure out which way is this grain leaning. And the way that I'm going to do that is we're going to do a cross-section cut on one side or the other, and we're going to try to see if we can see which way that grain boundary is going. So let's just tilt, we're going to rotate the stage by 90 degrees. Oops, what did I do? Moved. So here we go. And then we'll use the FIB to make just a cross-section cut, like right here. And that will show us what's going on with that grain boundary, at least hopefully. Okay, so here's our FIB image. Let's turn up our beam current a little bit. And because this is such a soft material, I'm just going to use a rectangle pattern. For something harder, you'd probably want to do the actual proper way to do a cross-section cut, but I think this should be fine. Now, one thing you can do is sometimes you can just watch the grain boundary here. So like I can see that here's the grain boundary. It's visible in the FIB cut. If I just kind of watch that as I sink down into the sample, that grain may move to the right or it may move to the left, and that might tell you which way the grain boundary is sloping. All right, I think we need a little more beam current. This is going a little bit on the slow side for me. Let's go up to 21. I just realized my image was not centered on this screen very well. Let's fix that. There we go. Okay, so we got our pit cut. Now in a lot of materials you'd be able to see the grain contrast down in here. Magnesium's kind of tricky because it doesn't really like to show it. One thing that we can do that might help is to do a cut at a little bit lower voltage, just to see if we can clean that face up a little bit. So I drop down to like 8 kV here. And let's just see if this helps at all. Okay, so don't really see the grain boundary yet. Let's try, we'll go a little bit higher voltage and we're going to go with a lot more beam current. Let's try like 3 nanoamps. Yeah, so I still don't see it. I can kind of see there's like a little bit of contrast down here in the corner, but nothing great. Right, so sometimes what helps is, let's do a little bit of rotation. Let's do like 2 degree. Hmm. So why I'm rotating is that sometimes if you get onto a different viewing angle on the grains, it will enhance the contrast between the two. Sort of like what we saw with the backscatter detector from the top down, where you had a lot of contrast. But I think maybe my cross section is just not good enough right now to show what's going on there. All right, so let's cut a bigger cross section. Or actually, before we do that, let's just try to clean up that front face a little bit more. All right, let's stop that pattern right there. We got a little bit of curtaining going on here, so to fight that, what we can do, here, let me save this position. We're going to do a relative rotation of maybe like 30 degrees or so. Not a whole lot. And then if we look on our FIB image, so the FIB is now like this. And now if we do a little bit more tilt, which I think we can get a little bit more, maybe go to like 55. So I don't think I didn't move far enough here. The idea is that what we're trying to do is let's do actual, go back to 52. Let's do a relative, let's just go all the way around to 90 degrees here. let's go down to like 40 degrees. So the idea here is about my fib is now coming in on an angle from the side of the cross section, and it should remove some of those curtains. So let's see how we did here. Not quite enough. So in a lot of materials, you don't need to do all this effort. A lot of materials, you do that simple first cut with the fib, and you can immediately see the grain. Magnesium's tricky. At least this sample's tricky. So. Okay, there, we've changed the curtaining direction. So now the idea is that the two opposing curtains will cancel each other out. We'll go with a little bit more angle here. So I think my FIB cut might be a little bit too aggressive. That might be why it's getting just constant curtains here. Well, I can certainly, there's that grain boundary right there. I think it's leaning this way, but I wish I could get it to show better. Yeah, this is a tough material. It's just really hard to see. I think I can see it there. All right, I think maybe the TLD detector is what we need. Okay, I'm reasonably sure I can see the grain boundary now. Probably, it would have been nice to have this surface a little bit nicer, but I think that's going to show up on your screen too. Yeah. Okay, so here's the grain, just in case it's not super visible. Let me put a line on it. It's basically right here. One thing let me try the digital. Digital contrast and brightness. There you can see it just by really messing with the settings. So here's our grain boundary. So it's almost vertical, a little bit of an angle to it. Now, I really don't like dealing with grains like this when they're really vertical. It's easy to miss them. So what we can try to do is we can try to kind of bias our lift out so that we're going kind of across the grain this way. I think that's probably the way to go here. New folder. I'm just going to save this picture just in case it is relevant. Actually, should save that one. Okay, so file, let's just say open. So there's our grain boundary. Let's So that ended up being 2 kV and 1.6 nanoamps. And a lot of messing around with the FIB, which probably wasn't as strictly necessary, but it worked out. Now I'm curious if I just go back, if I just cut that at 30 kV on an angle, if that would have showed the grain boundary. Um, so I can kind of see it right there. Not super clear, but let's try go into the high resolution mode with that TLD detector, see if it shows up. Yeah, it does, of course. So I wasted a lot of time, I guess, messing around with that low voltage. I guess the key there was just get on the angle. Well, it does have worse contrast than it did. So we take a really nice slow scan here. Well, I contaminated that face a little bit with the scanning, but you can see the grain boundary angle there, and that's kind of the important. That's the important thing. So that's good. It's a nice and straight boundary on a little bit of an angle there. All right, so let's proceed with our cuts. Now, when I go to do my lift out, let me is there like a pattern here? The normal kind of our normal wedge would be something like this, right? Equilateral triangle, and we would do this lift out Um, you know, just like this. Let me turn this brightness down a little bit. So that would work, but then it's really tricky to know exactly how to be right down that boundary, especially because the idea is we're not going to be able to see it very well. So what we can do is I can try to do my lift out on an angle like this. And now I know that grain boundary crosses through the whole width of the sample, and I shouldn't have as much trouble doing the prep. Now, how much of an angle we have to do here is subjective. I would say something like this shouldn't be too hard. This is basically like a 40, it'd be almost a 45-degree angle coming across there. And if I look, I've rotated my pattern to line that up about 20 degrees, right? Minus 20 degrees or so. And that should make this a little easier to target. So I think this is what I'm going to try to do. I'm gonna bias my lift out by 20 degrees, and so that instead of cutting at a 22-degree stage tilt, which would cut at the plus and minus 30 degrees, I'm going to shift everything over. So I'll be cutting at a 2-degree stage tilt on one side and a 42-degree stage tilt on the other. But then to do the lift out, I need to do the lift out also biased. So instead of lifting out at 0 degrees, I'm going to lift out at 20 degrees. So let's see if we can figure this whole thing out. So I think, and this is where you can play all kinds of games in your mind trying to do these geometry things. So I want to bias the lift out basically the way it's sitting in here, and hopefully this will make more sense. This is what I get for talking and thinking at the same time. I want to do a relative 90-degree rotation. Okay, so in this view here, the grain is, let me go back to actual. All right, so in this view, where the grain is, we're perpendicular to the SEM, so the grain boundary is just like this, which means it's starting here and it's sloping this way as we go down. And if I were to tilt the stage to 20 degrees, like I planned, you can see here from these pits that now the SEM is, let me coming down, let's see here. So I was like this. This was my vertical direction. Now I've tilted 20 degrees. So now the sample is going to be like that. No, that's wrong. I tilted it this way. So that, I believe, is the wrong, that's the wrong way to tilt. Because that makes the grain boundary more vertical. I want to be going the other way. So I need to do a relative 180. Okay, here we go. So now I've tilted. If I want to do the lift out in this position, and that will have tilted that grain boundary a little bit, and maybe even like 20 degrees. I could do even a little bit more, like maybe 25, 30 degrees, something like that, just to make it easy. Let's just do 30 degrees. Let's make sure everything's going to work out okay. So now since this is going to be my lift out position, I need to then do my undercuts with the FIB at plus this angle plus and minus 22 degrees. So this angle plus 22 degrees would be our 52 degree tilt, and the angle minus 22 degrees would be 8 degree tilt. All right, let's get rid of all these save positions so we don't get messed up here. So add. So this is our base position. So let's go to 52 degrees, and we'll do this cut first. All right, so here's my sample. Let's go ahead and turn up our beam current. Now, just to make sure here I don't mess up again, let me open up that picture, and let's put our polygon on here. So I'm trying to get a 2.5 micron. It's a 2.5 micron. Okay, so there's our lift out. It's relatively small. Maybe we can zoom in here a little bit. And what I've done is I've taken this and I've rotated it 20 degrees this way. So if I go in advanced, and I can say rotation 340 degrees. No, I did 30 degrees, 330. Okay, so here's my lift out. And you can see this angle is almost vertical, which makes sense because I'm at 52 degrees, so the fib is parallel. So this first cut, if I center, and I've got my platinum deposition is basically centered on the grain boundary right now. So if I do the cut like this, that boundary is going to end up way over in the corner of my lift out. So what I want to do is I need to kind of slide my center of my fib cuts down a little bit so that grain boundary ends up more in the center of the triangle when this bar gets picked up. So I want to be a little bit closer to the edge on the top side than I normally would, and I want to be a little bit out here away from the platinum on this side. All right, so take our fib image here. let's make sure we're in focus, because focus and astigmatism are important here. All right, and then we're going to do kind of a standard cut would be go a few microns wider than the bar on either side. In this case, let's add 3 microns each side. So that'd be 16 microns. I'm going to do 3 microns and 2 microns for Z. And again, we want to be like right up on the grain boundary here when we're all done and cut. So. Oop, I got another pattern somewhere. I got these polygon patterns. All right. To be honest, if you have the choice of any grain boundary in the world, sometimes it's easier to just go find another grain boundary that's not quite as vertical as this one was. But I guess this is a training video. I'm going to show, I guess I'm showing all the tricks here. And I guess if you're going to use that EBSD map I took at the beginning, keep in mind I'm reorienting the sample by 30 degrees, so all those orientations are not going to be absolutely correct anymore. And I just thought of another thing we got to be careful of, because I have to do the lift out in this orientation. Normally I would cut the left side of the pit free, and that's where I'd attach the probe. If I'm not careful, I'm going to have this thing fall off into space because I've got this giant pit over here. So when I go to do the cut on this bottom side, I need to make sure I don't cut through here. I got to leave some of this material behind, and I might even have to sacrifice a little bit of the end of this bar so that this thing has something holding it on onto the wall right here. All right, so there's our first cut. So let's say position 1. So now what we want to do is we're going to go to our, let's just go back to position 1 here. So we're going to go to this position. We're going to do a relative 180 degree rotation. And then we're going to tilt back 22 degrees. So we'll go to 8 degrees. And again, I don't want to cut through all this because I don't want that thing to fall. We can save this position as well. There's a hole. All right, so now what we want to do is clean up our edges. So let's drop our beam current down a little bit. Because it's magnesium, it's pretty soft. All right, first, here, let's cut the end off where we're going to attach the probe. That's this guy right here. Okay. And we'll do a little cleanup cut up here. Now remember, this is the side. I don't want to get too close to the platinum on this side because I will, by doing that, I'll shift the grain boundary way over. So I just want to clean up just the bare minimum on this side. Okay. Now we'll go back to position 2. And so this side, I want to be a little more aggressive because I can come up a lot closer to the grain boundary here than the other side. Okay, and then I'm going to do one more cleanup just because all that cutting will probably have contaminated this bottom side again. So let's go back around to position 3. And we'll just go ahead and trim this one more time. Okay. We should be all set now to do the lift out. Now, if you've never done a lift out with the stage tilted, don't be afraid. It's not that much different. Just use the same procedure as you always do. So I'm not going to show the Autoprobe software. I have it up on the support computer, but if you're watching this video, hopefully you already know how to do a lift out. Otherwise, probably everything I'm showing you is not making a lot of sense. Okay. Now, I always want to make sure my FIB and SEM are lined up well. All right, close enough. Let's remove all of my positions. I'm going to add one more position here. Now, just to be on the safe side, I want to make sure that I don't crash the Omniprobe into the lift out. So I'm going to bring the Omniprobe in. I move the sample way off to the side, and I'm going to check my Omniprobe position just to make sure everything looks good. Okay, let's edit our eccentric point. We'll go to eccentric high, and we'll take out the Omniprobe. We'll go back to our save spot. All right, let's go ahead and bring the Omniprobe back in. And I'm going to use the carbon injector for the weld. I like to use that one for this procedure. I'll still use platinum to connect the sample to the posts, but okay, there's the probe. A little bit big. That's okay. We'll make it work. Oops, running into the corner there. So gotta be a little bit closer. Probably should have cut that back a little bit more than I did, but this will be okay. I want to fill in that crevice with the gas. All right, that should be connected. And let's turn up our beam current and we'll cut this end off over here. Nope, not PT dep, I want silicon. Should be good. Do a little shake test on the mic. Oh, no, it's still connected. It didn't wiggle. So where are we connected? I'm going to cut a little bit more here. It might be because I got it sitting on this corner. I don't like doing this, but I think the probe is resting on the corner of the sample, which is why it's not wiggly. Yep, that was it. So we're all set. Go ahead and just go straight up with it. Even though that sample's not inclined, or it's not flat, it's on an incline, you can still just go straight up with the probe. Get it up away from the pit, and we'll send it to park. All right, so now what we're gonna do, we're gonna vent the chamber, and we'll put the TEM grids in. I didn't mention that, I'm putting these on TEM grids this time. So those will go in the chamber, and we'll drop off the samples, and then we'll have to actually vent one more time, I think, so that we can get everything set up for doing the TKD stuff. So let's go ahead and vent. And we'll pause this recording so that you don't have to watch a ton of empty space. Okay, we're back. Chamber's pumped down. And so now, so I've got two copper TEM grids in here on my, this is my kind of homemade TKD holder that I'm going to use to hold on to these. These grids you'll see have been previously sharpened using the plasma FIB. I'll make a video on how to do that at some point, but it's not too terribly difficult. You basically just cut the grids from the top down with a big beam current. And the idea is to make them into posts, just like the silicon coupon posts that are used for conventional atom probe. So you see here I've got flat top, copper grid, all right. Now, I want to set this up so that when I bring that lift out bar in, the bar is horizontal, but that means the grain boundary is also going horizontally. When I go to look at this with TKD, my beam direction is going to be this way, and I want the grain to end up parallel to that direction. So I don't want to drop the samples off like this. I want to turn this 90 degrees so that the samples end up with the grain boundary going this way. This would be the same approach if I was going to do TEM on these sharpened tips. I would set it up like this too. Okay, so we link our working distance. Let's double check all of our alignments here. There it is. These copper grids are nice in some ways, but for some reason they always tend to block all your signal to the detector. So for some reason when you do this, you never get a really good image on them. You see it's super bright over here on the left side. Maybe we can try a different detector. But anyway, not a huge problem. All right, so we got our post. Let's go ahead and bring in our Omniprobe. And this time I am going to use the platinum injector. I find the platinum works the best when you're trying to attach the Atom Probe samples to these posts. Just it's more electrically conductive. It works better than the carbon does. If you had tungsten, I think tungsten would work fine, but we don't have tungsten on this tool. Now, the top of this sample is going to be on a weird angle, but hopefully if I did it right, the bottom is still symmetrical and should sit down on this post correctly, if I did it right. I've definitely done these before where if you do the angle the wrong way and you end up making a really weird looking sample. So well, hopefully today is not the day for that. And these are copper posts, so you see here all the grain structure is going to show up in the copper. Okay, got it set down. And we'll go ahead and put half a micron of platinum in there. Sometimes I do 0.4 microns. I think the gas injector is starting to run out on this tool, so I'm just going to give it a little bit more just in case. I want to make sure these get stuck down. Okay, let's turn up our beam current, and we'll cut this free. Okay, 1 down, 3 to go. Now, normally I don't go all the way up to eccentric high with doing this, but because I got to go over top of these big posts, I'm a little bit nervous about it. So I'm going to kind of like take every step I can to go around everything here, because I don't want to crash. So I have 2 posts on each TEM grid, and they're on the outside positions. So we've got 2 blank posts in between. And then when I was on the PFIB, I actually cut a notch into one post and I cut 2 notches into another one, so you can tell the difference between the grids when you're in the Atom Probe, or in the TEM, I suppose. Use the beam shift, get that yellow crosshair right on top of the post center. That way you know right where it's supposed to be. There we go. Okay, so now just because we got to go a long way to get to the other grid, I'm going to take out the probe and the gas injector, and we can slide our way down to the other grid. It's right here. So this should be post 3. Yep. Now this piece is getting a little on the small side, so I'm going to try to get two out of this one, but the last one's, that's way off center. Usually the bottom, you want that to hit right in the center line of the post. Otherwise it tells you you're probably not lined up right. Okay. I'm going to shift this one over just a little bit. Okay. Yeah, I think our platinum is almost out. These welds look pretty ugly to me. But I think we got enough to get through today at least. And a little thing on the bottom of that lift out there. I don't like that. We're going to cut that off. Why not? We have a FIB. Fix. What is... Alright, now we cut the probe free. Alright, so now we have to weld the other side. So we're going to do a 180-degree rotation. And we'll just come on back down the row of these things and put a weld on the back of each one. That one doesn't look very pretty. I don't know what happened to this guy. Well, you don't win them all. All right, 2 more to go. All right, one more. This one. Yikes. I don't know what happened to the side of this guy, but so the next step in the process will be I'm going to have to vent the chamber and transfer this holder over to my pre-tilt stub. So in order to do the TKD most effectively, we want to be able to tilt the samples past 50 or past 60 degrees. We'll get just a better TKD quality there. So this holder I have built that's in here right now has a 45-degree pre-tilt part that goes on the bottom. So we'll set that up, and then we'll do all the sharpening with the tips on that holder, just in case there's any change in angle or anything like that when they get moved. I think before we vent and change though, let's do a quick little cross-section cut on each one of these things just to make sure the grain boundary is where it should be. So that way I'll know if I'm wasting my time or not. I should see an image that's pretty similar to what I have down here in quad 3, except it should be, if I did everything correctly, it should be rotated 30 degrees clockwise relative to what this one is. And hopefully that boundary is going kind of through the middle of the chunks. Okay, take the gas injector out. Let's do a -90 rotation. Let's just go back and start on tip number 1, why not? All right, let's go to 52 degrees. Okay, so if we did this right, I kind of see the, I think I see it right there, but let's, we're going to use the FIB, just this nice kind of small beam current here, and we're just going to clean up this front edge with a little rectangle cut. And all this material will get cut away later when we do the sharpening anyway, so I'm not sacrificing the integrity of the Atom Probe tip by doing this, as long as you don't cut too much off. Well, if that's the grain boundary, I did pretty good. I'm not quite so confident that that's it. But let's trim back just a little bit further. Yeah, that's what I thought. Okay. So, however, I do see there's a little step right there. That's probably where the grain boundary was etched. So if I want to see it, remember we were in the high resolution lens mode. And we need a little bit more beam current. Well, not so visible, I suppose, but you can kind of see the little step right there going up. So I'm pretty sure that I've got it. I got the grain boundary there. So the boundary should be going like right across here. Maybe some of those other posts will show it better. All right, so not a great image here, but I'm worried about damaging these things, but I think you can see that. Pretty sure that's the grain boundary right here, which is pretty much right where I want it, right down the center. So that's good. All right, so let's go ahead and we're going to change this over to the TKD holder, and we'll get to sharpening these things. Just like before, I'm going to pause the recording because you don't really need to see the chamber venting. All right, so we've got the sample back in the system, pumped back down again. You can see here, this is the my TKD holder. So it's just the same holder that was in there before. So it's a TEM grid holder on a height extender, and then it's on a 45-degree support. And then this whole thing has been ground down to make it smaller. That reduces the issues you have when trying to do TKD. All right, so let's go ahead and find our samples. So let's just start with post number 1. So on this particular holder here, I have my marker post. I either cut with two slots or 1 slot. So this one, so you see I have single cut on this one. So that means this is post 1, or this is TM grid 1. This would be post 1. So we'll go ahead and let's drop our beam current down. And as always, we want to focus, link our working distance. We'll go to 4 millimeters. That doesn't change for any of this process. Now, if I want to get really lined up with this thing, what I'm going to do is first, here, let's do an XT align feature. And we're going to make this horizontal. And then we're going to tilt to 45 degrees. And at this condition, I want my holder, these lines ground on the holder need to be horizontal. So those are actually pretty close. Sometimes they can be a little bit off though. All right, so now what we're going to do is let's go down to 7 degrees. And this holder has some clearance issues, so I'm going to turn on the enable safe stage moves, and then we're going to do a relative compucentric 180. Okay, so at this point, these posts should be pointing right at the fib. We can check that out, of course. So they're a little bit off. We can play with the angle slightly here. It goes the other way. Let's go 6 degrees. Yeah, I think 6 degrees is good enough. So a little bit off. You always pick up a little bit of mistakes when you reorient everything, put them in new holders and whatnot. Okay, so let's go ahead and we'll get these sharpened. So I'm going to partially sharpen them all, and then we'll do the TKD stuff. All right, so let's go ahead and say update. This is going to be post 1 FIB. Post 2. All right, so just getting all these saved positions in here. Post 3. And I'm calling these the FIB positions versus, we're going to have EBSD positions as well, or actually TKD later on. So I want to make sure I have the ability to bounce back and forth between those spots efficiently. All right, so let's just go to post 1. And we'll start cutting. All right, so the first step I'm going to do a 2.5 nanoamp cut. Let me see, do I have my, yep. All right. So I think I'm going to change my angles a little bit here. So I want to make sure I don't cut away too much of the post. All right, so we do a circle pattern. And we'll do 6 microns to 2 microns. We'll do 2 micron deep. And remember that I wanted to kind of bias everything towards the left side here. That's so that the grain boundary is more in the center of the tip. So let's kind of slide this over here just a little bit. And this edge sticking out here on the left is going to get wrecked because there's no platinum over it, but it doesn't really matter. I just want to make sure that the center line of my sharpening process goes kind of right down the center of this volume. Oh, my tilt correction is way off because I forgot to say I'm on a 45-degree pre-tilt. Actually, it's really a 51-degree pre-tilt, I guess. No, 47.5. There we go. Okay. So let's see, can we see any grain boundary type things in here? Not really, but you can see where the boundary is right there, and I think it's going on an angle about like that. So we should hopefully be in decent shape to catch it if we go right down the center line. All right, so this is number 1. We're going to update number 2, change that to be 4.5. Okay, save. Now let's go to post 3, 5. Okay, update number 3. All right, now this one's sitting a little weird on the post. You can see the center line of the sample's over to the right a little bit. So I think I still want to go after kind of like right here. Okay. So what we're going to do now is drop our beam current, drop our pattern size down, 3 micron to 1 micron. And did I update? So this one is a little suspect. I don't see the little step in there, but I guess we'll just have to go for it and see what happens. I think we got a good chance that the other ones are going to work out. I think we need to shift this one over a little bit. I'm going to have problems. This one got really off center for some reason. This was that last one that I dropped. Last one I set down, and even then when I set it down, I said something's not right about this tip. I don't know what's going on here, but it doesn't look good. So what we'll try to do here is we'll do this sharpening step, and then we'll go and see if we can see the grain boundaries using TKD. I think the bottom edges of these samples must have oxidized because they're glowing, which means that this thing is charging up. So maybe this is a film of magnesium oxide that formed on the bottom before I got it attached. It makes imaging these kind of weird. Didn't get a very good bond on the weld right there. Let's see if that fills back in. I might have to go in and patch that. Like I was saying earlier, I think our platinum gas injector is almost empty, and when it starts to run out, you get stuff like this happening where you get weird inconsistent patterning and bonding and stuff like that. So okay, so let's turn this down to our next step. Should be 80 picoamps. And we're going to do 2 micron to a half a micron. We're going to go in about 0.2, maybe 0.3 microns deep. Not very much there. So let's go ahead and set up our EBSD. Now I know for TKD we're going to want to be at 30 kV. And we're going to need more beam current for this. All right, let me shrink this guy out of the way. All right, so let's all right, so first of all, we got to tell the software that our image area, we're on a 47.5 degree pre-tilt, right? Because that's, yep, 47.5. And that should let us put the camera in. Actually, no, it's still going to yell at me, but that's okay. I know it's safe. So I'm going to say insert camera. I suppose I should probably move this out of the way somewhere. Let's just put it over here for now. Okay, so the camera's in. What's up, team? Did you crash on me? I think team might have frozen up on me. All right, I guess we get to reset team. So we need to go find team EDX. Where is it? Team EDS. And boop. Let's try this again. Try this again. Camera's going back in. All right, so let's do our live scanning here. And if we look at our camera, hopefully we can see something. Now I'm going to use some settings that I know worked in the past. I'm going to do 2x2 binning. And we're just not getting any signal right now, are we? We need more beam current, I think. So one thing we can do is let's go and tilt a little bit higher. So let's do a relative um, right, so now we're at 70 degrees. There, now we're getting some patterns. Okay, so let's turn this down a little bit. Turn the gain up a little bit. And then for image processing, I'm going to use this custom recipe. And we're going to modify it. And the big one you want is dynamic background subtraction. And then we're also going to do, I like this guy. Let's just try those two and let's see if we can get a pattern off of this guy. So we can go to, first we got to set up our sample. This is going to be post 1. Oh, right, we got to change it into TKD mode. So TKD mode, and our angle off of horizontal right now is 20 degrees. We'll just do a really kind of a big step for these is like 0.2 microns or something, because let's see, are we actually getting some patterns? Yep. So we're actually getting some patterns, and it's actually indexing it. And we can see that there, but it looks like we got our grain boundary. So let's play with this a little more. Let's make our step size a little smaller and bring this guy down just a little bit. So it's not indexing really great right on that boundary for some reason, but here's our grain boundary right here, pink to blue. So it's actually good. It looks like it's biased a little bit more to the right. So now what we're going to do is we're going to add a position here. We'll call this TKD post 1. And what we're going to do is we're going to go thin this guy down a little bit more and then come back and check it. Make sure we're doing okay. Now we don't have to take out the EBSD camera as long as we don't do any giant crazy moves here. So and as these get smaller, as it gets thinner, we might be able to actually do the TKD at this 52 degree tilt. But for now, we'll just go ahead and do it this way. Hide that. Okay, so I want to be a little bit more to the right this time. Okay, so let's save this, and let's say this is post 1 FIB. Let's update that because it moved a little bit. So we'll go back to our TKD position. Okay, and we'll say image area. We'll try this again. Let's see. I'm going to have to do something about this crevice right here. This is going to cause trouble. So now that this is a little thinner, this hopefully will be a better quality map. I usually turn off the image quality map. It usually doesn't show much of anything for these tips. So here's our grain boundary right there. And then we've got obviously some nonsense going on down here at the bottom where okay, so the grain boundary is still like right in here, which is great. That's kind of right where we want it. So let's go on to the next post and we'll see how that one goes. So we'll go to post 2. So this will be post 2 TKD. We're going to change our sample. Post 2. Now it's all the same grains, right? So every one of these should have a pink grain on top and a blue grain on the bottom. Otherwise, we got some weird things going on here because they all came from the same grain boundary. So this one, it's got a really big thing down the middle there that doesn't want to index. So something with that, the grain boundary. But we still have our grain boundary here. This one is maybe a little bit more vertical than the other one was. So, but we kind of want to go right down the middle, I think, on this one. All right, so post 2 FIB. I'm running out of time here, so I might only just do these 2. Let's see how it goes. File, save as. Post 2. Alright, so this one will go right down the center. Oop, don't zoom in. All right. I'm just curious about, let me see if I can actually index this guy right in this spot. Maybe I can. Now that it's thinner. Okay, so I got a ton of background signal. None. All right, that looks like that's pretty good. Let's try it. Oh, I forgot to change my tilt angle here, so now we're at 38 degrees because we're parallel to the FIB. Okay, let's see what happens here. Hey, yeah, it's indexing. So we got our pink grains there. And the blue grain. Now if you can see this, notice the SEM image in the background and the EBSD map don't line up really well. There's something with the scanning, how team does scanning at these real high magnifications. They don't ever line up. So I always make sure you make your map area a little bit wider so that you make sure you get your tip contained in there. All right, so things are going well here. So let's drop our, we're going to get rid of these FIB ones, or the TKD ones. We'll just do it at 52. So we'll remove TKD spot here, remove this spot here. We're going to update our FIB spot. And we can go up number 3. I don't know why we're way off here. So number 3. All right, so we can say image area. Oops, stop. We gotta change our sample. Sample. Those 3 inherit structures. Image area. Now this one may not index so great because it's thick and we're on a pretty steep incline. But again, at this point I know what colors I'm looking for the grain. So as long as it turns pink, we're good. And it did. So we got our pink grain on the top, and we've got the blue grain on the bottom, so we still have the grain boundary. A lot of nonsense here in the middle. I'm not sure what that's about, but here's the boundary right here. It looks like it's offset more to the right a little bit. So I think this one, we want to sharpen it, bias a little bit to the right, if we can. I'm saving, yeah, post 3. Nice. This one's going to be a good one, I think. I got the grain boundary. It's nice and centered in the post. It's indexing well. I like it. All right, post 3. Let's go look at post 4. All right, I gotta do my map first. This one, sample post 4. So we definitely got the pink grain on the top. Yeah, so this one, I'm not really sure how to interpret that. It looks like there's some of the grain boundary over here to the right, but it's definitely not as pretty as the last tip. But let's just try maybe the grain's like right here. So we can try our best. Definitely going to go over here to the right hand side of this one by a lot. Like maybe way over here. gonna let that one run for just a few more seconds. I want to get rid of this little shoulder here in the deposition. That kind of stuff can cause trouble. All right, good enough. All right, so let's go back here. Let's check it, see if we did any better. Look at that. You can see the TKD map quality gets a little better as these posts get thinner. So this one should be good. The grain boundary is way down here in the bottom, but it's there. And that's what we want to see, because once we have a map like this one, let me pull this one back up for a second, right? Because now I know that that grain boundary goes across the entire width of the tip. So now all I got to do is thin it, and then when I do my low voltage cleanup, I have to keep track of when I get close to this boundary, and then stop at an appropriate spot. But that's a lot easier than trying to find the boundary in the kind of the X and Y directions. So we're going to do one more cut here at 30 kV. We'll go 1.5 to magnesium's pretty soft, so maybe I'll do like a 250 nanometers. And then I think I'll do maybe like 0.4, I'm not sure. Let's see how it goes here. Update my position. Okay, so just right down the center for this one. What I'm looking for is to kind of remove the this kind of extra thickness up here in the platinum cap. The magnesium's so soft it's going to cut away beneath it. I'm not really worried about that. There we go. And you want to try to avoid having these little steps form down here in the platinum. So that was, what did I do? I did 0.16 micron depth. All right, so let's see how we're doing here. This should be even better quality scan because now it's super thin. You see we don't really get anything up here in the top where the platinum cap's still there. So then here is the grain boundary. Okay. Looking good. So that's number 4. Let's go back to number 3. So we gotta do sample. So post 3 should be just kind of right down the middle, just like that one was too. We'll do 0.16. I like that. Okay, I like it. Let's see, mapping. I realize now you can't see anything I'm clicking up there, but you should know. Hopefully, whoever's watching this knows how to run the EBSD software. Okay. That looks pretty nice. We got a platinum cap, top grain, bottom grain, lower weld, platinum. That looks good. Number 3 is in good shape. Let's go look at number 2. Sample number 2. Okay. Now, I guess I didn't mention it, but you don't need a very high resolution EBSD map for doing this, because most of the time for this kind of work, you're going to have just two grains in that tip, and they're really, you only need to see where the boundary is. You really don't need to have like a really beautiful map to do this, but you can certainly turn the step size way down if you want to. It just ends up taking a long time. I'm sure we could mess around with the camera settings, get this running a little faster, probably. Maybe kick it out of 2x2 binning and go to like 4x4 binning or something. Turn that exposure down a lot. Let's see if it... Yeah, not quite as pretty, but it works. Another thing we could do is go up and beam current here a little bit. So one nice thing on the Helios is you have lots of beam current available, even without losing too much resolution. Yeah, I don't really like that. I like my original settings. Let's just go back to those. This is just going to contaminate these tips really bad at this beam current. Let's see, 2x2 binning, and turn the gain down a lot. It works for me. so hopefully I didn't completely destroy this tip. All right, post 2, update, post 1. Right, this one we need to do some work down in here. So what I'm going to do is we're going to put in the gas injector. And we're just going to scan our SEM in there. And we're going to pop open the platinum injector for just a second. Fill that up with platinum. That's all it takes. Pretty easy. Now, unfortunately, that platinum is going to stick around in the chamber for a while, and it's probably going to contaminate all the tips going forward. I hope not. But it happens. And yes, I didn't do another TKD map on this one. I'm pretty sure these are going to be fine at this point. I need to get this done. Once you know where the grain boundaries are, there's really no point in overdoing the TKD stuff. It's just obviously if you really want to, you have at it, but the big benefit is going to be when we do the low voltage sharpening to remove that platinum cap and to target the final ROI for the Atom Probe tips. That's where we need the TKD to be scanning all the time, which is coming right up. So let me change my sample over here to post 1. All right, so we're going to go to our low voltage cleanup now. We're going to go to 5 kV. I like to use 68 picoamps. We can check our alignment a little bit here. It's pretty good. Okay, so I'm just going to do a rectangle pattern, about 3 micron by 3 micron rectangle over top of the Atom Probe tip. I usually like to make the pitch a little smaller than the default. And we're just going to use that to go after the grain boundary. Now, I usually want to have the grain boundary end up about 100 nanometers down from the end of the tip. So let's go ahead and we'll just take our picture here real quick. And we'll need our TKD map. So we'll come over here, we'll do image area. And let's take the step size down just a little bit here. maybe drop down to like 50 nanometers instead of 100. Okay, so there's the grain boundary. Okay. So it's, the whole thing was 2400 nanometers down. All right, so let's just let this sharpen for a little bit. We should be able to watch this live. Yeah. So grain boundary is kind of right in the middle. Expand this so you can see it better. So I've got my mouse kind of where I think the grain boundary is. So once that platinum cap leaves, this thing's going to probably start to shrink a lot quicker because that magnesium is pretty soft. All right, let's stop. Let's take a look. All right. Okay, so we're still almost over a micron from where that grain boundary is. So we keep going. I think I'm going to shrink this pattern down a little bit. We can make it go a little faster that way. Obviously our tip is getting a little bit weird shaped here. So this one, maybe my step size is too coarse because it looks like the pink boundary, the grain boundary is like right here. It's right at that shoulder basically. Which that shoulder is still a long way down. Okay. All right. So zoomed in a little bit here. That step size is way too small. Let's go 20. Okay, there's the grain boundary. So I don't know if I trust this measurement tool. Yeah, I guess it's right. All right, so that means we got to go further down here. sometimes the image quality gets kind of low here, so it's almost easier to watch the little live camera display, and you can see where the boundary is because the Kikuchi bands switch. So still about 500 nanometers from the end of that tip. I think I'm gonna drop my voltage down on my FIB. I think maybe a little bit lower voltage will help this one. Just because magnesium's so soft. So now I'm sharpening at 2 kV. Okay. So here's the grain boundary right here. So now we're like 400 nanometers down from the end, which for magnesium it might run that far. Could probably, maybe if I dropped my SEM voltage down a little bit, maybe I could get those maps to index better, but for what I'm doing here, it doesn't really matter. As long as I can see what I'm doing here. So we're just going to take a little bit more off the tip. I'm going to stop it. I'm going to call this one good. We'll do one more final map on this one. Save image area. Let me see if I can drop my step size down a little bit, see if I can get a little bit prettier map for the kind of the final result here. You know what? I just realized something. There was something I forgot to change. If you go into the Huff parameters, oh, these are already up. Usually I do the defaults and then 120 and a half. Let me see if that helps at all. Not looking very pretty, is it? But actually here, this image quality shows a boundary pretty clearly right there. So according to this, it's still 700 nanometers down. I don't know. I think this is fine. I don't trust these numbers. I think these numbers are wrong. All right, so let's move on. We got to do tip number 2, and then I got to quit. So post 2. So we'll do this one with the 5 kV. So this thing on the top is all the platinum. Okay, so that grain boundary is still way down at the bottom, right down here at this shoulder. So I've got my mouse cursor sitting right on where I think the grain boundary is. So We'll just let it come down until it gets there. All right, there's the grain boundary. It's still about 500 nanometers away. So I'm going to do a little bit more cutting here. So I'm going to try to get a little closer to the grain boundary on this tip. Maybe like 200 nanometers or so from it. I think we're going to do a little bit more. Let me take off like another 100 here. Okay. Starting to get some weird little steppy things here. I don't know. Maybe that's something associated with the grain boundary. Okay. So yeah, I think for this magnesium samples, at least, the image quality map seems to be kind of the best way to see it. So yeah, right in there. This should be a good one. All right, so we're going to call this done. And one last thing I'm going to demonstrate is the stem detector, which you have to have the right sample holder in to do this. But I'm just curious, kind of curious if this is going to show up or not. So we need to take out the EBSD camera. So pull that out. Okay, so you see we're up here at got our sample flat now. Put it in the stem detector. Stem dark field. Electron beams, stem, high angle dark field. Let's see if any of these show. All right, there it is. 'Cause, 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 almost looks like there's a film on that boundary. All right, so that one I could probably, it would go a little bit longer, I think, if I was really into this tip, but these are just kind of practice tips. File, save all. Anyway, I could take a lot better image, but I'm worried about contaminating the tip with carbon. So I'm going to leave it kind of as is here. Let's go, let's see what that other tip looks like. Maybe that one looks good too. So this one looks like it might be a little further away. It's about 350, similar. So this is post one. All right, let's vent, call it a day. Tracked.